Howdy! Most likely, Spire 2 is easily one of the biggest games ever made on Godot. It was built by a studio that famously showed off a middle finger to Unity, scrapping 2 years of development and rebuilding the entire project from scratch in a new engine. And probably MegaCrit was one of the loudest voices in the industry calling out Unity's disastrous runtime fee policy, and they backed up their stance with a complete engine migration, which ended up with a huge commercial success. But that's not all of it. Not only MegaCrit basically invented the roguelike deck builder genre, what makes them even more based studio is that they are completely okay with their code being decompiled and studied. That's why, in order to honor this spirit, today we're diving deep into the source code of Spire 2, so we can see how exactly a top-tier studio structures a project of this scale. And once again, to keep things simple, I've divided this video into 3 chapters. In the first chapter, we're going to explore some gameplay-related code logic, hidden mechanics, and a few funny details I have found. Second chapter is all about technical side of the code. We're going to look at the netcode, enemies AI, card storage and execution logic, feedback tool, and a generally well-written AutoSlay bot that's used by the devs for an automated QA. And finally, in the third chapter, we'll break down the overall code architecture, point out some pros and cons, and of course we'll look at some design patterns used in the code. However, before we start, I want to make it clear that I am not a C# pro and game dev is one of my hobbies. Although I am a programmer, but I usually spend my time coding in Rust, so take it with a grain of salt. And with that being said, let's start with a question you've all been asking about. How exactly the stupid mantis picks the card to steal from your deck? What's the code logic? Well, it's all inside the file fivenhopper.cs, and here we can straight up see it has a variable that is literally defined as steal priorities. By the way, not gonna lie, the code of Spire 2 does contain tons of funny names for functions and variables, which means developers had lots of fun writing it. Okay, so upon picking a card, Mantis clearly does not roll your rarest card. Instead it runs down a 4-tier wishlist. Thus the order goes uncommons first, then commons, rares or event cards, then basics, and finally imbued cards. Question is, why does it target uncommon cards first? It seems like it doesn't make any sense. But if you ever played Spire, you probably know the answer. I mean, what actually makes your build to work is usually an uncommon cards, not a flashy rare. That's why a stupid mantis deliberately tuned to rip out a card that you would miss the most. Of course, within a tier it picks randomly, which is exactly why it feels like it knows your favorite card. And the countdown above its head is a special power called Escape Artist, although the counter isn't what makes it flee. As we can see in the code, fleeing is just a hard-coded 5th move of this enemy. It means that the only reason counter is here is to make you panic. Mantis also pins a little picture of the card he's going to steal to make you feel even worse about it. I suppose whoever designed this enemy at MegaCrit had lots of fun doing it. Now, if you ask me, I think one of the most interesting parts of the game is the map generation. I always wondered how exactly it works in the code. Is it fully random? Is it deterministic? What's the entropy then? With all those questions in mind, I've started digging the code for answers. Okay, first of all, there are currently 4 acts in the game. Each act has its own code file with a class derived from base act model. And by the way, the difficulty settings are actually hard-coded here. Say an underdogs.cs or overgrowth.cs sets base number of rooms to the value of 15 and the number of weak encounters to 3. And for the unknowns and rest, it uses a custom function called nextGaussianInt. It generates a random number that leans towards the middle instead of being flat. In this case, it will return either 6 or 7, with approximately 60% chance for the 7 to be rolled. There is also a hidden deprecated act. It seems like it was cancelled at some point, but the file is still present. I've also found a scripted events logic in the code. And as you probably might expect, new players' first run is always quietly scripted. There is a variable called number of runs that tracks how much runs player went through. If, say, it's your very first run, the first 3 unknown marks on the map, the question marks, will always be the same. First 2 of them are going to be events, and the third one is going to be a fight. Funny enough, the events you get and that fight are also hard-coded. Events are Bird's Nest and Sapphire Seed, and the fight is whatever enemy is currently in the hard-coded sequence. And yes, your very first run are guaranteed to be Overgrowth. And apparently, it also defines a set order of rooms for the first run only. I mean, even the rewards you get playing as Ironclad are also hard-coded for the first run. By the way, whenever you open your very first chest in the game, it will also provide a fixed relic. There is even a log message saying forcing specific relic because it's the player's first treasure chest ever. All of this means that new players are guaranteed to experience a beginner-friendly first run to ensure a curated introduction. Now onto the map generation code itself. From what I can tell, it's fully deterministic, meaning the same seed will produce the same map every time, and the entropy for RNG here is a Unix time. However, it isn't that predictable, because it gets seeded only once at the very first call. Later calls advances the RNG stream, but they don't reseed. The clock is read only once for the whole game session. Thus, in theory, it could be possible to manipulate the run seed by changing the clock on your PC, but in practice it's a bit more complicated. The clock only needs to be on the right second when the game starts, so probably one could freeze it for some time. I mean, I haven't tried it myself, why would I? So the map generation algorithm itself consists of, like 6 stages? Let's get through all of them so we can fully understand how it works under the hood. At the very first stage, the code defines the dimensions of the map, 7 columns with 16 rows, with the player's starting point set to row 0 and the boss pinned at the top. For some unknown reason, it also makes the map 1 row shorter for the co-op, but I guess it's a deliberate decision to make co-op runs feel more balanced in terms of pacing, I guess. Next stage decides how many special rooms will this map have. Remember those files we discussed earlier, and the function called nextGaussianInt? Well, that's where it all lands. After that, the code traces the roads for 7 separate paths from the bottom row up to the top, each starting from a random lane. It also forces the very first row to have at least 2 choices, so a player can have a choice right from the start. And then, because each path climbs 1 row at a time, at every step it can also go up, up left or up right. So it picks one of those 3 choices at random. Of course, it also performs a validation so that 2 rows will not cross each other. Finally, this stage makes sure to wire the ends so that each node on the last grid row gets a boss as a child. So no matter which opening you pick and no matter which path you take, you end up at the boss. Now, stage 4 is an important one. It defines each room type, but beforehand it sets few rooms as follows. The top row is always a rest site, 1 row is the treasure, the very first row is always a fight. Everything else gets randomly set based on the current map data, like n rest sites, 3 shops, 5 elites, a dozen of question marks, etc. Excluding the fights for now though. It also involves what I call a 5 placement rules, which is no rest elite below row 6, no extra rests in the top 3 rows, no 2 of the same key room directly connected by a road, no same type child, by the way, apparently this specific rule is a redundant one, and finally, no 2 of the same rooms sitting side by side in the same row as a branch options. And finally, it fills all of the left unassigned rooms with the fights. Next, at stage 5, the code tries to find any repeated segments of the map. Same shape, same rooms. It's required in order to prevent them from feeling boring. So the code hunts for those duplicates and then deletes them. And if that deletion happens to contain, say, an important room, a shop for example, then a quick repair pass converts one of the fights into the shop or whatever key room it had. At stage 6, the map is basically ready to use. However, it performs a cosmetic cleanup so it's nice to look at. It centers the grid, pushes crowded rooms apart so they don't overlap, and straightens some of the jagged rot visually. That's how map generation works in Slay the Spire 2. Hey guys, I'm recording this while editing the video. A few days ago, Slay the Spire 2 apparently received a major update number 2, and one of the things they changed is how RNG works. Now, instead of the default system random, they use mega random, which is a Xoshiro256 algorithm, copied quote-to-quote with heavy modifications from the Redzen library by Colin Green. In their Steam blog post, they explained it quite well. Turns out their separate random streams were secretly correlated, so one role could leak info about another. The new RNG removes that, so the randomness is finally fair, and that's true. However, personally, I see one more reason behind this. Microsoft doesn't promise you that system random will always produce the same sequence. I mean, they already changed how it works once between versions, and they reserve the right to do so again. And for the most games and programs, it doesn't change a thing. However, for the game that must be deterministic by its nature, that's a game changer. And if the dice could quietly change under a Windows update or something like this, that can break tons of things. So I guess it's the second real reason why they swapped to Xoshiro, a well-known public domain random numbers generator. Feed it the same seed and it will always generate the exact sequence on every machine, every platform, every version, every time. And while I am not a C# expert, I know that Xoshiro256 was introduced in .NET 6, but if I remember correctly, it works only on the unseeded paths. Correct me if I'm wrong. Anyways, I thought that's something you might wanna know, so let's continue. Okay, you might think MegaCrit has a huge quality assurance team, and while maybe that's true, one specific QA member team stands out. That's because it's integrated into the code of the game, a special module called AutoSlay. And essentially, that's an automated bot that can run thousands of seeded games with only one job: find bugs, glitches, softlocks, desync issues, anything that can break the game. Looking at the code, we can see that it acts as a real player. It selects a random character and then plays through an entire run with a custom seed. Funny enough, it doesn't try to pick the best way to play. Its card selection brain is kinda dumb, but I guess in a good way. It shuffles the list of valid options and then blindly picks whatever there is. AutoSlay doesn't try to win, which is a brilliant solution for QA, because it forces the game to playtest thousands of pure RNG deck combinations, thus helping devs to find weird edge case bugs and glitches. By the way, this is how it looks in the game. AutoSlay plays, let's say, quite fast. That's because it's programmed to skip some of the delays. And when it actually does get stuck, a watchdog timer runs out. Then it prints a full state dump and reports the failing seed, which then can be manually reviewed by the devs to fix the bugs. However, probably most surprising thing about MegaCrit's test bot is that it has no special access to the game, no special API. It plays the game exactly like a real human who can only see the screen. Because when it needs to click a button, it doesn't call any special function. Instead, it traverses through Godot's scene, grabs the button and simulates a real click. So if a button stops wiring for whatever reason, the bot will break exactly like a real player. And for this to work, it utilizes Godot's UI helper. It can work the subtree recursively, simulate a click and find any element on the screen. Once again, a brilliant solution. And as a programmer, let me tell you, man, I like automating boring stuff. If you ever heard a joke about programmers spending 10 hours automating a 1-minute job, that's literally me. Cause I want to focus on the core logic and I hate tedious stuff. But when a project requires pulling a live, real-world data from search engines, automation usually grinds to a halt, because writing custom scrapers is nearly impossible. And if you ever done it yourself, yourself, you know the pain. Constant rate limits, changing HTML output, dump capture requests. I'm getting flashbacks even talking about it. That's where today's video sponsor SERP API comes in, as they provide a clean, reliable, and fast search results from Google, YouTube, Bing, and more through a simple API. So all you have to do is make a request and get a clean JSON response with all the data you need. And guess what? You don't have to worry about proxies, rate limits, or anything else. So whether you need an easy access to Google Images API to gather a dataset for your next huge ML project, or say you're making a search results ranking tool, SERP API handles all of it. Get started with 253 credits by clicking the link in the description below or scan the QR code on the screen. Once again, thank you SERP API for sponsoring today's video. And with that being said, let's continue with our code breakdown. Okay, now I bet you didn't know that literally all of your fights are being recorded by the game, even when you play solo. That's a hidden replay system I found in the code. Although currently it's used only by the feedback tool, that we'll also discuss later in this video. What that means is that each run could have a full replay snapshot of every fight plus every action taken in it. However, at the current point, it only ever saves the latest one and the end of each combat inside a file named latest.mcr. There is even a special developer menu with a file picker that lets you open an MCR file and replay it, which is exactly how MegaCrit reproduces your bug reports. And we can even test it manually right in the game. As you can see, it straight up replays my last test fight, without me touching any of the input devices. At this point, I had only one question in mind. Could MegaCrit ship a full-blown run replays? Honestly, the answer is probably yes, most likely, because the code already does all the hard work, records all your actions, it just doesn't save them all, which means they could probably add this feature in one of the upcoming updates, so you can analyze your runs better. I mean, there is already a mod called Run Replays that adds this feature. Although it's a bit broken, but thankfully it's open source and I have an experience with Harmony, so I fixed it. And then of course made a pull request so you can check it yourself as well if you want to. By the way, this is how it looks in the game. You can watch a full replay of a run at any speed. Looks dope, not gonna lie. I hope the developers will add this in one of the upcoming updates. Anyways, while reading the code, I've also came across some funny stuff. Say a function that is literally named do hacky things for specific powers. And by the name only, you would probably never tell what it does. As far as I can tell, it's a hand-coded patch for one specific family of powers, like the Misery card, that applies all of the enemy debuffs onto each other enemy on hit. However, debuffs like a temporary strength are a bit tricky to deal with, since it secretly applies a real permanent strength too, so copying it to 5 enemies basically sets 5 real strength stacks, which is an issue. Do hacky things for specific powers function tells those powers to skip their hidden side effects just before the copy, thus it avoids any unnecessary side effects. There is also one specific relic that actually can accuse you in cheating, and it's a sea glass relic. When you obtain it with no character attached in the code, which is a state that normally shouldn't happen, it will write a message to the log saying, "This is either our bug or you opened the cheat console." Although it doesn't crash and don't punish the player in any way possible, if that's the case, the code just assigns Ironclad as a character. For some reason, the code also contains a basic profanity filter, but as far as I can tell, there is no co-op text chat in the game, so what's the purpose? Man, you're gonna love it. When the game rolls you a random seed for your next run, it re-rolls it until the generated seed doesn't accidentally spell something rude. And let me tell you, the list is quite cautious. It even includes some of the blasphemy. And probably the last funny finding I thought it would be interesting to include in the video is a special trailer mode that is apparently used by the marketing team at MegaCrit to capture a game without any of the UI elements. It comes with a bunch of debug keys as well. Say number 1 on the keyboard will hide the top bar, 2 will hide intents, free for the combat UI, etc. Trailer can also slow down or vice versa speed up the game, and the U key can be used to unlock all of the playable characters. Okay, now let's move on to the next chapter. Of course, team at MegaCrit implemented common code techniques and optimizations such as object pooling, sprite atlasing, node graphs, singletons, etc. But I suggest we focus more on the code architecture, design patterns, storage logic, netcode, and overall Godot implementation, especially since we know the code was migrated from Unity mid-development. So probably the very first thing I noticed is that Spire 2 doesn't have a central game loop. Instead, it advances through an async coroutines over the action queue. Just don't confuse it with UI updates. They do run through Godot's process function, but every single one of them are for visuals only, and they tick 60 times per second. However, the main game logic that usually runs through a main game loop simply doesn't exist. Godot's root node endgame has no process function. Combat Manager and Run Manager doesn't have one either, and they aren't even a Godot node. Those are plain C# singletons, and absolutely nothing in the codebase pulls them each frame. Instead of this, the entire game logic relies on an async coroutine that advances over an action queue. Thus, every single thing you do, playing a card, drinking a potion, picking a reward, even clicking on the map node, is packaged into a little object called a game action, which is then dropped into an ordered queue. There are only 11 types of actions derived from game action that you as a player can perform. Basically, it means that everything in the game is built as a serializable ordered commands list. I mean, yes, at first glance it seems like an overkill, but honestly, that's a brilliant solution. You get a free deterministic combat replay system and, more importantly, a perfectly synced multiplayer pipeline, since all you have to do is to keep that one list in sync across machines. Of course, that's a bit simplified description, but you get the idea. Although, keep in mind, you don't want this system if you're making a basic game for a jam project, since it can confuse beginner developers. But we can't argue this approach is hella good one. Like, say you want a replay system, bam, you have it all for free. Wanna add a multiplayer? Send the list across the network. That's it. Want to make it so nothing runs while the player thinks? Well, since there are no logic loop, it means the whole thing is asleep until the next click. And the cherry on the icing is that you don't have to build any of that right now, but you've left the door open for all of it. And that's exactly why MegaCrit built this system in the first place. Now, since this game supports multiplayer, the code should follow certain rules and best practices in order to keep things perfectly synchronized. So let's look at some online related code. And I think I'll put it this way. The three pillars that makes STS2 netplay work are decimal maths, assorted shuffle, and the JIT prewarm. First of all, we can see that they constantly use a decimal type for gameplay maths. Take the final HP and block values, those are plain integers. However, the calculations are done in the decimal type, and it's a deliberate decision, which is used to prevent floating point desync in multiplayer. And because float arithmetic can produce different results across different hardware, using a decimal, which is a base 10 floating point type in C#, guarantees identical results no matter the environment, because it's a software implemented and fully specified. Although that's not a unique thing, since pretty much all of the online games with a deterministic lockstep netcode model do something similar, and I thought I should explain this. By the way, for those of you with SQL background, don't let the naming confuse you, cause decimal in C# is not a fixed point type, unlike decimal in SQL. The card's shuffling code is also worth looking at. By default, the game uses a Fisher-Yates algorithm. Basically, it iterates through an array and swaps the current element with a random one. But because it shuffles things based on their current position, the output is entirely dependent on the initial state of the array. And for a multiplayer game, that's an issue. Because if two players have the exact same cards but in a slightly different internal order, a standard shuffle immediately causes a desync. So, in order to address this this issue, developers wrote two separate functions, unstable shuffle and stable shuffle. Stable shuffle guarantees determinism by forcing the cards to be sorted first, and only then it shuffles. The result is, of course, a perfectly synchronized output across all of the clients. Although the start and draw pile is built with an unstable shuffle, that's because it comes straight up from the deck in the deterministic order, so no pre-sort needed. A JIT pre-worm is also an interesting one, and it has a direct impact on a multiplayer. So basically, as we know, lockstep model waits on the slowest client, and if a client hits an uncompiled serializer mid-game, it will cause a JIT compile right away, which can lead to a frame stuttering and a lockstep that waits for the input. And as far as I know, JIT compiler in .NET performs a quick tier 0 compile on first call, so the hitch is smaller than a full optimizing compile. However, in order to solve this issue completely, developers introduced a JIT pre-worm during load screen, which leads to a much smoother multiplayer experience. I mean, yeah, it's not a determinism thing, the whole game would stay in sync perfectly even without it, but since JIT only pre-worms network packet serializers, it's still pure netcode, and I thought it would be interesting to let some light on this topic as well. And probably the last question I've been asking myself about netcode here is that whether MegaCrit uses some sort of a framework to implement multiplayer, because in Unity we usually use things like Fishnet, NGO or Photon, and the answer is none. Of course, I am far from being a Godot expert, but I can't seem to find any traces of a popular high-level net framework in the code, so I assume that the whole netcode was written by hand. MegaCrit used a Godot's built-in init library, a reliable UDP protocol, and for Steam they used the Steam networking sockets through steamworks.net package. That's the whole network transport used for multiplayer, which exactly lines up perfectly with everything we discussed so far: custom serialization, decimal math, and desync workarounds. A fully handwritten netcode that also happens to work perfectly. Great job, MegaCrit! Now let's break down the enemy's AI, because it's far less complicated than I thought it would be. Funny enough, there is no special boss brain in the code. Elites and bosses shares the exact same logic basic slime does, and they all use pretty much the same FSM named monster move state machine. So basically, there are three archetypes for the enemies in the code, which can be also combined together. Those are fixed pattern archetype. The enemy has a graph with a chained moves that repeats in a loop. Good example is a Shrink a Beetle. It applies Shrink, a one-time debuff opener, and then cycles through chomp stomp like a ping pong. Weighted random archetype. The enemy rolls a dice to decide its next move. The basic Act 1 Flyconit is a clean example. It rolls among its 3 attacks each turn and never repeats the same one twice in a row. Conditional archetype makes the enemy react to something, its own HP, a status, its position, etc. The basic swarm enemy Nibbit is probably the best example. It picks a different move depending on whether it's alone or standing in the front of the pack. And as I said, some of the enemies can combine the archetypes to form a more complex behavior. However, the only 2 enemies in the game that combines all 3 archetypes at the same time are Exoskeleton and Fabricator. Honestly, I thought that would be a test subject or a queen or at least a waterfall giant, but they only utilized 2 archetypes, although they all have 8 nodes, which makes them the most complex enemies in the game. Waterfall Giant specifically is the biggest and the dumbest one at the same time. It has 0 AI branches with a single long fixed chain of 8 moves. By the way, if you want to reproduce the same AI behavior engine in your Godot project, you can do so literally in under 100 lines of code. And I am not joking, it's that simple. Now, the next thing we're going to break down is a bit more complicated. Let's look at the core game mechanic, specifically how exactly cards are stored in the code and what happens when you play a card. And probably the single most common wrong guess is that a roguelike deck builder of this scale should keep the cards in a CSV file or a big JSON file. I mean, it sounds right, things like this should be data-driven. Well, Slay the Spire 2 shows a middle finger once again, because every card here has its own C# class defined in a separate per card file. A card's damage, block, cost, keywords, rarity, and behavior are all inside the code. And let me remind you, this game has approximately 577 cards, which means there are 577 CS files for every one of them. However, there is a registry that puts them all together, an instance of ModelDB class. At GameBoot, ModelDB's init function walks every abstract model subtype and makes an instance of it. For the base game, that list is a generated static table which contains approximately 1600 models. By the way, a model's ID is just a slugified class name. But it doesn't mean that there are no data files at all. Don't forget about localization. Card's display name, description template, flavor, etc. The code uses data-driven approach for this, and it all stored in the JSON file. Funny enough, every number on the card, damage, block, applied to vulnerable, isn't a plain value. It's a little object that secretly stores three versions of itself: the base number, the number after enchantments, and the number to actually show on the screen right now. And that's exactly the trick behind cards like Strike, whose displayed number increases with your strength and the enemy is vulnerable, while the card still quietly knows its real damage value. So, in order to increase the base, you obviously have to actually upgrade it. That's how it works in the code. Oh, and I've probably just quietly moved from card storage logic to the card's execution logic. Anyways, that was the plan. Okay, first things first. Your hand is capped at 10 cards. Try to draw more and it'll slide into a discard pile. And a card itself can be in one of 6 places: draw pile, hand, discard, exhaust, play, deck, or just none. Each of those 6 is a card pile object that wraps a real list of cards. For some reason though, the card itself doesn't really know where it is. Ask a card which pile are you in, and the code will iterate through all piles until it finds it. Of course, compared to other approaches, this one is kinda much slower. However, at the same time, it means a card can never lie about its location, and the piles are the single source of truth. When you play a card, I guess the logic behind it can be divided into 3 separate steps, with each step being quite important. Everything starts with a click of a mouse. However, it does not directly play the card as you might expect. What actually happens is that it calls a try manual play function, which then checks if the card is legal to play and then calls for enqueue manual play function. Basically, the code here builds a play card action object and pushes it to the queue. So by clicking a card, you make a request for an action, but not the action itself. And it's quite a big difference actually, because it matters a lot for the multiplayer to stay synced. Although even in solo runs, the same system still applies. Now, at the second step, when the queue reaches your action request, it calls for execute action function. But don't let the name confuse you, since before it actually plays the given card, it performs tons of different checks. First of all, it rehydrates the card from a network handle back into a real card model. Then it checks if the card is still in hand pile, if it can be played, if the target is valid, etc. So once everything is okay, a function spend resources gets called, so you pay for an action. And finally, it builds an instance of game action player choice context class and calls for onPlay wrapper function. Now we are actually ready to play the card. So here at step 3, a real card execution engine runs. It pushes the card to a play pile. Then it asks 2 questions. Where should this card end up afterward, and how many times should it fire? Next, the play card loop happens. Each iteration here builds a new card play struct that carries things like card, target, result pile, play count, etc. Then it runs the following sequence of function calls. Before card played hook, card play started history log write, card's own onPlay function, enchantment onPlay function, affliction onPlay function, card play finished history log write, and finally after card played hook. And after every single step in this sequence, it checks if the card's owner is defeated and returns early if so. Funny enough, inside the code, the game doesn't differentiate between a player and the monster you fight. They are all named as creature. Anyways, after all iterations are done, card gets moved to a different pile. Which one though depends on the result pile type field. It can be either removed from the combat, exhausted, or by default moved to a discard pile. And that's pretty much how it all works. Once again, if you ask me, it feels a bit too verbose. You gotta wrap around the wrapper, calling an action through a queue that then does a ton of other things. Say, on-play wrapper alone literally performs 6 different jobs, and there are some dry issues that bloat things further, and possibly some parts of the pipeline could be simplified a bit to make it somewhat more straightforward. However, this is what a good game code looks like. It's boring, and sometimes even paranoid about timings. Honestly, I didn't had much fun reading it whatsoever. So let's move on to the more interesting stuff. Now, some of you might be interested on how exactly the feedback tool works in Slay the Spire 2. Trust me, it's far more complex than you could imagine. So, when you hit send feedback button, the game assembles a genuinely thorough case file, which then gets uploaded to MegaCrit as a zip file. It contains a feedback text, a selected feedback category, a game version, exact git commit, per launch session ID, and even a screenshot downscaled to 720p. A zip file also contains your last combat replay file alongside all of your save files and the most recent crash dump. By the way, that replay file lets developers to rerun your exact fight on their machine and watch your exact bug happen. However, what I genuinely respect is the privacy work here, because most studios skip it. You see, before anything gets uploaded, 2 filters in the code cleans up the logs. One replaces your Windows user folder and the other finds every Steam ID and swaps it for a random number. This way, a developer can still follow steps to reproduce your bug, but they can never recover who you actually are, which is a good thing. And the feedback uploader code is also actually quite polite about failures. It retries on server hiccups with growing delays, gives up gracefully on a real rejection, and, this is an important detail, doesn't spam its own crash reporter when the real problem is just your Wi-Fi being down. Oh, and for a successful report, you get a cartoon flower nodding at you. That's cute. And now we can finally break down the overall code architecture of this game. Slay the Spire 2 contains approximately over 3k CS files across more than 200 folders, plus 23 GD script files. The overall codebase is also quite clean. Core/models for the state, cards, powers, relics, all lands here. Core/nodes for the view, all the nodes are located here. Core/commands for the API, damage commands, attack builders, etc. everything located here. Core/game actions for the player intents, play card action, network card rehydration, those are all here. Core/hooks for the hooks system. And the same goes for multiplayer, saves, random, map, rooms, runs, etc. You can almost read the entire engine's responsibilities just by looking at the directory list. And there are also 2 quite heavy compile time source generators that produces 2 files. Abstract model subtypes.cs, a 5k lines of code file whose only job is to touch every model type at least once. So a .NET trimmer can see each abstract model subclass as used, thus refusing to delete it. And the second one is MegaCrit serializer context.cs. This one contains, like 13k lines of code, and as far as I can tell, it's a save file JSON serializer, built at compile time instead of a runtime, for whatever reason. Honestly, for any beginner Godot devs out there, you might want to skip some of the implementation paths of Slay the Spire 2 codebase. Say, for logic view split, you can use a resource for data and a node for the view. Godot already gives you this for free. A resource is a plain data object with no scene presence, and the node is what you actually see on the screen. Instead of a custom singletones, you could use a Godot autoload feature. STS2 handles run manager instance because it needs tight control over lifetime and networking. You don't need that. Godot's autoload gives you a global you can reach from anywhere as GameState.something. For the action queue, most of the games can use a straight-up function call. The whole thing about wrap every click in a game action and put it through a queue exists so that network clients agree on order. So instead, just play the card directly and announce results with signals so the UI can react. Finally, instead of generated serializer, you can freely use Godot's built-in save tools. For data as resource saver and load handles it quite well. And for the save blob, you can use var to str, str to var, or just JSON. I mean, as you can see, some of the decisions inside Slay the Spire's 2 code most likely comes from a previous Unity codebase, and some parts of the complicated code are only here for the sake of multiplayer. Make sure to keep that in mind. Now, probably one last thing I also look for reading the code is a design patterns. And while I'm usually not a huge fan of things like OP or Solid, I'm always all in for the design patterns. I believe sometimes they can make your code like 10x better. And of course, as you might expect, the code of Slay the Spire 2 contains tons of various patterns, but I suggest we focus on the most interesting and proper textbook implementations. First and most obvious is the command pattern. Say, inside the bash.cs file, we can see this line of code. Damage CMD here is a clean example. It doesn't hit the target directly, instead it builds a command. Separate object that describes the attack. What, how much, who, only then it fires with execute. And as a bonus, it also reads like a sentence. That's pure sugar on top. Another good example is prototype plus flyweight design patterns in one place, specifically inside the abstract model class. There is exactly one master copy of each card sitting in a dictionary. So when the game just needs to read the card's name or a base damage, it reads that single shared copy instead. And nobody is allowed to change it. That's the flyweight. But when the card needs its own state, it clones the master by calling member-wise clone function with a deep copy of its fields. A function called mutable clone is all responsible for this, and that's prototype. And of course, there is also an object pool pattern present in the code, and you guessed it, it's used for the card nodes. Although the clever part is the way pool gets cleaned. When a card goes back inside the pool, the code walks each card's signal connection and unplugs it manually. Thus, the recycled card can't accidentally still be wired to a dead screen or 5 ghost events. And I thought that's a tiny interesting part I should mention. Next up, we got a strategy pattern inside AutoSlay QA bot. And if you look at the code, you will not see a gigantic if-else sequence or a switch case. Instead, it keeps a lookup table, so each room type maps to its own little handler object. A shop handler, a combat handler, an event handler, each one is an interchangeable behind a shared interface. You walk into a shop, it grabs the shop handler. You hit a card reward screen, it grabs that screen's handler. Thus, each handler is represented as a single swappable strategy. This way, whenever you want to add a new room type or a special event, all you have to do is to add exactly one line to the lookup table and write a handler itself. Easy! That's the power of interchangeable algorithms behind the shared interface chosen at runtime. Just like I said, patterns are a cool thing to have in your sleeve. Anyways, that's it for now, and it wraps our video today. Once again, I would like to give a huge shout out to MegaCrit for allowing us to access the game's code, because they didn't obfuscate it, thus allowing us to make mods and learn from the code much more easily. And if you want to support my channel, I have a Patreon, link in the description below. Or you can just subscribe to the channel, there are plenty of related videos coming soon. I'll see you in the next one, and as always, have a great day!